Right. Hi, everyone. Thank you for attending the talk, and sorry for the snafu earlier, mix of time zones. So I work at my lab at Princeton is called Vertaix, and we have started working on using AI for natural science problems. One tool that we are very fond of that I worked on earlier is generative modeling. So today I'll talk about trying to answer are tractable probabilistic generative models more diverse. So this talk is about evaluating generative models, which I think we don't look into as much as we should. So what are generative models? I'll use a very simple definition of generative models, meaning a generative model is math that tells you how data was generated. So if you're looking at probabilistic generative models, that will involve using the language of probability as a way of defining sampling, but it can be anything else, like a simulator, for example. I would define that as a generative model as well. There are two main families of generative models in the literature, a family that's called tractable probabilistic generative models. So these are things like autoregressive models and deep latent variable models that variational autoencoders optimize and things like that. And there are implicit probabilistic generative models. The main one you probably know about is generative adversarial networks. And basically the difference is that in tractable probabilistic generative models, you are able to not only sample, but also evaluate the likelihood of a given sample. Whereas for implicit probabilistic generative models, all you can do is generate a sample. You define a sampling process for data, and that's your generative model. For generative adversarial networks, for example, you define the sampling process by saying, let's draw a noise variable from, let's say, standard Gaussian, and then we pass that variable through a neural network, and the output of the neural network is our sample. The usual way we also distinguish between these two families is that tractable probabilistic generative models tend to be stable to train. They're also known to have lower fidelity. I say known to have with this tilde to say that may be a stereotype, quote unquote. Things aren't always clear cut like that. Tractable probabilistic generative models are also can be also easy to sample from. So, for example, if you take the generative model optimized by VAE, you just take noise and then pass it through, sample through some prior distribution, pass it through a neural network, and then add noise, and you get the sample from that generative model. So that's very fast. For implicit probabilistic generative models, they're known to be unstable to train. Generative adversarial networks in particular are very unstable to train. There's been a lot of work that's done on that. They're known to have higher fidelity. Again, I put a tilde here because that may be one of the stereotypes between these two families. Sometimes it's not always true. And they're also easy to sample from. One stereotype that I'll focus on here is the one that says tractable probabilistic generative models are more diverse than implicit models such as GANs. I myself believed in this, but we started working on evaluation for diversity, and it's not always the case. So let's go through that. Let's start with what we want out of a generative model. It's a generative model. We want for it to have high fidelity to the domain. So if the domain is text, we want our generative model to generate coherent text. That's what I mean by high fidelity. If the domain is images, we want for our generative model to generate images of high quality that are high resolution and sharp and visually appealing. We want for our generative model to be stable to train, and that will allow us to train big and flexible generative model, especially needed if the domain is very complex. So that's a desideratum. We want for it to be easy to sample from. It's a generative model. Our goal would be to get samples from it. Let's say that that's the main use case. So we want for that sampling process to be easy. And the main desiderata here in this talk will be diversity. We want for our generative model to be able to generate diverse sets of candidates in the domain. And why do we need that? Why do we need diverse generative models? Mainly the thing that I'm interested in is for scientific discovery. For example, when you're looking at active search strategies to find new drugs or new molecules, you would want for the sampling process to be diverse. You want to be able to sample rare events. That's one characteristic of diversity, not just focusing on the main modes of the distribution, but also regions that have low density. You want to be able to sample from that as well. That helps in discovery. Having a diverse generative model ensures some sense of fairness. For example, if you have images where you have faces, most of the data sets we have, it's faces with light complexion, but for those faces where the individual in the picture has darker complexion, our generative models tend to not sample those because they tend to be the rare data points in the training data. And so we do want diverse generative models because we want for our generative models at test time to be able to generate all those types of faces. So there's a sense of fairness there, and there's been work that was done on that. We want diverse generative model for effective data augmentation. In many areas, generative models are used for data augmentation so that you can train models in different domains, especially when you don't have labeled data. So that's one use case for generative models. And for data augmentation to be effective, you'll need to be able to generate diverse samples. To give more choices to users, so for things like image captioning or anything related to generative modeling for us, you want to be able to generate different options so that the user can choose which one works for them best. So diversity comes in play there. And also finally, model-based RL, you want to be able to generate diverse trajectories. So hoping that we are in sync that we need diverse generative models, let's track back and think about what actually diversity means. What does diversity mean? We will borrow from the field of ecology, studying species. So in that field, the diversity is defined as the effective number of species in a population. You take a population of birds, the diversity is defined as the number of unique birds in each family of birds. I don't know if that makes sense, but yes, that's a very intuitive definition of diversity, and that's what we will build from in order to propose an evaluation metric for diversity in generative models. Because if we are able to evaluate generative models for diversity, the hope is that leads us to build more diverse generative models and helping in all the ways in which we want to use generative models. So given this definition in ecology, let's go through a bunch of desiderata for a diversity metric. It should be capturing effective number, meaning a population containing n equally abundant, completely dissimilar species should have a diversity score of n, the total number of species in the population, when they are all very, very dissimilar. And if all species in the population are identical to each other, the diversity should be at its minimum. It should be 1. Another desiderata for a diversity metric is partitioning. So suppose the population is partitioned into subpopulations with no species shared between subsets. So these are distinct clusters of species. Then if the species in each subset is completely dissimilar from the species in any other subset, the diversity should be entirely determined by the diversity and size of each subpopulation. Then there's the desiderata of identical species, meaning if 2 species are identical, then if you merge them into one, the diversity shouldn't change. The fourth one is monotonicity, meaning that is a very intuitive one. When the similarities between the species are increased, the diversity should decrease. And there's symmetry, which encodes a bunch of things. One of them being that diversity is unchanged by changing the order in which the species are listed. So order doesn't matter. And diversity should also be left unchanged if you're relabeling. What I mean by that is, if you have two sets of populations, one is, say, dogs, cats, and rooster, and the other one is chair, table, fridge, then as long as the abundance in each of these clusters is the same, the diversity shouldn't change. So the fact that you're in a population of cats, dogs, and rooster doesn't matter. It doesn't matter. So let's look into the diversity metric that we're proposing to evaluate generative models. Consider this quantity HQP, which is the Renyi entropy of order Q. It's 1 over 1 minus Q log of a sum over I in support of P of Pi to the power Q. Here, I in the support of P just means that we're only considering those points for which there's a positive mass. So we're not considering anything that's assigned a 0. A Hill number is the exponential of this Renyi entropy. It's called a Hill number. And it's just taking the exponential of this. So you end up with sum over I in the support of P, Pi to the power Q, 1 over 1 minus Q. Now the metric we are proposing is the Hill number of the matrix of eigenvalues of a kernel matrix. Here we will be considering the similarity between all the data points and using that as a kernel. So you give me a similarity measure, a similarity metric. I have all these samples x1 through xn. I compute their similarity matrix. I have an n by n matrix. I take its eigenvalues. I order them by decreasing order, and I take the Hill number of that matrix. That's the diversity metric we're proposing, and we prove theoretically that it has all the properties that we just went through. So I'll show you a bunch of visuals justifying the metric. Somebody is asking a question. Okay, this is something else. We will go through a bunch of visualizations about the properties of the metric and when it captures and when it doesn't capture. And you'll see that actually some metrics that are proposed in the literature to capture diversity, there are not many of them, but even the ones that are ubiquitously used, such as average similarity, they actually don't capture these intuitive notions of diversity that we naturally want. For example, here, consider this figure on the left. The way this was constructed is we define the space of data points as space of shapes and colors. So shapes are these ones that you see here, the diamond, the trefoil, and these ones. These are the shapes. There are 4 of them. And then the space of colors. So, you know, this is fuchsia, magenta, and yellow, and black. And so you have that space, and the kernel in each of these 2 spaces, color and shape, is defined as kernel is 1, the kernel entry is 1 if the 2 data points have the same color, or 1 if they have the same shape in the other one, and 0 otherwise. So what you're seeing here on the left is the identical species property, which is that if 2 categories are identical to each other, then combining them into a single category should leave the diversity unchanged. So that is the case for the diversity metric we're proposing. The diversity metric we're proposing is the one where you choose Q equals 1. Remember what Q was. Is here. Q equals 1. When Q equals 1, basically, all the species are weighted by, the diversity is weighted by the species in the abundance they come in. That's when Q equals 1, and that's the one we will be using throughout all the experiments. Here, when I say D1, that's the one that I mean, choosing Q equals 1 in the metric that I just showed. And you see that it satisfies that, and that is not the case for into div1. This is internal diversity. It's the main diversity metric that is used in generative modeling for molecules. So you see that it increases when you use the same species, but you just add them together. So this is an undesirable property that these existing metrics have, which the metric we're proposing doesn't have. Then there's this other experiments about modularity and replication. So if two equal size populations are completely dissimilar from each other, the diversity of the combined population is equal to the sum of the diversity of each subpopulation. So the metric we're proposing satisfies that, whereas the main existing metric, internal diversity, which is some form of average similarity. I didn't define it. It's actually defined as some average similarity score, the one used in generative model for molecules, and also used a lot in NLP. Think about average similarity using Blue as a kernel score. That's also what's used in NLP ubiquitously to measure diversity. And it turns out that those types of scores don't capture these notions of diversity that I just mentioned. You can see that going from these two to the third one, that you're actually summing the diversity score from each of the first clusters, which is what we want. That's not the case for IntDiv. Another thing to test is completely dissimilar species. So in this block A, you can see that the metric is capturing actually the number of effective species in the sample. So here there are two modes. The diversity metric is 2. There are 3 here, it's 3. 4 here is 4. The IntDiv is also increasing, but there's no notion of interpretability in what these scores actually mean. Whereas you get that interpretability in the metric we're proposing. We don't have a name for it yet. That's why I'm calling it the metric we're proposing. If you have a name proposal, please send it to us. And this second experiment is that when you add more complexity and that you're in a noisier setting, where no two samples are completely identical, some are close, similar, but not completely identical, then you still get the effective number of modes. We computed these numbers. They are not integers necessarily, so 2.17, 3.18, 4.14. And again, internal diversity is increasing, but it's not, there's no interpretation as to what this means. We applied it to different domains. We applied the metric to different domains because it is domain agnostic. In any domain where you have a similarity, a notion of similarity, you can apply this metric to measure diversity. So we applied it to a bunch of generative models for molecules. That was the first domain. Then we applied it to a bunch of generative models for text. Then we applied it to a bunch of generative models for images. And comparing, and in all these models, you'll see some that are tractable probabilistic generative models and some that are empirical and gram ones, and some that are implicit generative models. So here, let's look at the application to the generative models of molecules. We took there's a benchmark for generative modeling of molecules called Moses. It has a bunch of the proposed generative models for molecules. It's like the papers with code where you have a bunch of state-of-the-art generative model for images and things like that. So this is the equivalent, but for molecules. So we took all of those models and we compared internal diversity, which is the main metric for measuring diversity for those generative models, and then compared it with the metric we're proposing. What's good with this is that it only depends on a notion of similarity. So you don't need a reference distribution to compute the metric. And you're able to actually compute the diversity of your original sets of data. We do that here. So the target here is forward C, the diversity in the original set. In the original set it was trained on. And the generative models are listed here. So there's a variation, the variational autoencoder. I don't like to call it a generative model, it's an inference method, but understand here by VAE, it is the generative model that was fit by a VAE. It has a score of 0.856 under the internal diversity metric and 475.3 under our metric, and compare that with the latent GAN here, which is, so the VAE one would be tractable probabilistic generative model, and the latent GAN would be implicit probabilistic generative model, And so you see that the above metrics assign the latent GAN to a higher diversity score than the variational autoencoder, and the result is more striking under our metric. And I think And I think this was very surprising because of the stereotype I mentioned at the beginning, that we've always been saying that GANs are less diverse than VAEs in general. But when you look at these state-of-the-art models and you generate a bunch of samples from them, and then you evaluate diversity over those samples with this well-defined diversity metric, it's not always the case that the GAN is less diverse than the VAE. Another thing that was surprising here is that showcasing why we actually do need a principled, well-defined diversity metric for generative models is that this main diversity score metric that's being used in the literature of generative models for molecule is assigning a very high diversity to the HMM model, which is the least diverse in our metric. And you can see that visually in the plot on this right-hand side, where you see that internal diversity is just is increasing just by a little bit from, this one is looking at the kernel matrix for 250 molecules randomly sampled from these models. And we're picking 536 because that's the one that's most diverse under our metric. And HMM is one of the most diverse ones under the internal div. And you see that there are replicas. There are a lot of replications under the HMM, which you can notice by the yellow shades of the plot. There are less of that here. And D1K, which is the metric you're proposing, is reflecting that difference by assigning a significant more amount of diversity to this model than to the HMM. That's not the case for the internal diversity one. So application to generative models of text, we applied it, like I said, to text generative models as well. Here is actually conditional generative models because we're looking at image captioning, meaning that you condition on the image and you generate a description for the image, a textual description for that image. So we compared mainly decoding algorithms for image captioning. So those are, the main one is beam search, but people have also proposed diverse beam search where you regularize beam search with a diversity inducing term. And so here what you're seeing is that, let's compare the blue. Blue is a metric in the NLP literature. I don't know if there are people here working on NLP that gives a sense of high fidelity score. Like if your blue is high, it means that the text is of better quality, more coherent than not. It's a very silly metric actually, because it's just taking n grams and comparing the overlap. But it has driven NLP forward. So despite the metric being not very satisfactory, actually, there's been, NLP has seen a lot of advances. So that was not that big of a problem. Now imagine if we have better metrics, what we could do. So compare that with n-gram diversity, again, overlap in comparing which ones are different, more different than others. The metric is saying, the metric we're proposing is saying that diversity is lowest with beam search and highest with diverse beam search, and even higher when the diversity regularizer on the diverse beam search is increased. So that is what is supposed to happen. And that's what we're seeing with the metric is at least capturing that if you go from beam search to diverse beam search, the diversity should increase, and the diversity should even increase more as you increase the entropy regularizer, which is the case here. So we also, under the same text application, we looked at looking at actually how does, if you had to plot different each image and the captions that were sampled for that image, and you, by beam search or diverse beam search, let's plot the quality as measured by sentence blue. So that's what you see on the x-axis. And let's compare that to diversity as given by our metric that's on the vertical axis. You will see that diverse beam search, which is the orange dots, correspond to the orange dot, tend to be more diverse than beam search, because you see them on top vertically, but they tend to have, diverse beam search tend to have lower quality as measured by sentence blue, because you'll see that when you go horizontally from left to right, you'll see more blue than you see oranges. So the metric is capturing that. Now we're looking at applications to generative models of images. So here we're reporting inception scores. So in the image domain, in vision, inception scores are the metric that measures quality of the samples. And FID is a metric that's been ubiquitously used, and it's measuring, it tends to capture some form of diversity, tends to capture some notion of diversity. So we wanted to see how the metric we're proposing fare under these different generative models of images. So here you have the GAN and compared with diffusion models on the ImageNet resolution 64 by 64, and looked at ImageNet resolution 128 by 128, and still with comparing GANs and diffusion models. And then you have the Elson bedroom resolution 256 by 256, and this time looking at style GAN versus the diffusion model, and then Elson CAT 256 resolution 256 256 comparing style GAN 2 with ADM. The way we came up with this table is that we looked at state-of-the-art generative models for a given data set that have been published, and where we have actually checkpoints published that we can just use and evaluate these different metrics on. So we didn't train the big GAN, we didn't train the style GAN, we didn't train the style GAN 2. We looked at the published checkpoint by the authors, published, and drew a bunch of samples from these models and computed the diversity metric on those. I don't know if that makes sense. So here you can see that on average, the diffusion models have higher quality scores. So again, this is GANs used to be, which are implicit model, used to be thought to be like to have the higher sample quality. That's not the case. So diffusion models have higher quality scores here, and they cover more of the reference data set, which Recall does measure. And the metric we're proposing, so D1K, indicate the samples from GANs are more diverse. Again, this is a surprising result, knowing that we think that GANs tend to be less diverse than other generative models. But for state-of-the-art models, when you go to like these large expressive models, things may not always be the same. And the good thing with this metric is that you can actually compute the diversity of the original data set, which we're reporting in these tables as well. And all these models, state-of-the-art, don't have the same diversity as the original data set. They are still all there's still a gap between these state-of-the-art models and the diversity of the original data set. So the takeaway from everything I said is that I hope that you're convinced that generative models should be diverse, and that we do want to build generative models that are diverse for all the purposes I mentioned before. And that I hope that the results have shown you that we haven't been measuring diversity correctly. We looked at the field of ecology, which cares a lot about diversity. That's the main thing that they study. We looked at that and came up with a new diversity metric for generative models that is domain agnostic. If you're in a domain that has a notion of similarity defined, which is in most domains, then you can use this metric. It captures all aspects of diversity that we talked about in the field of ecology and in our case as well, machine learning. And it's unsupervised in the sense that you don't need a reference distribution to define it, which some of the existing metrics do. Like for FID, you will need the original samples, and you fit them, you pass them through some inception, train the inception model, and then you use that and compute the Wasserstein descent. So you see that you do need reference distribution. Here you don't need it. That's what I mean by unsupervised. It's theoretically grounded. It's actually when Q equals 1, you know, there are all those special cases from the metric you propose, but when Q equals 1, you actually end up with a von Neumann entropy, which is the general entropy definition under in the field of quantum statistical mechanics. So it has is theoretically grounded and has well-defined properties and things like that match the desiderata for diversity we discussed. And we will make it readily available for Hugging Face in Hugging Face Evaluate, which is a hub for evaluating any model with any metric. So we'll be making it available there so that you can start using it. But basically, I think we should pay more attention to evaluating generative models, and hopefully this is a useful endeavor. Thank you.
Thank you for this very inspiring talk. We have time for 1 to 2 questions. Who has a question?
Thank you, Adji, for amazing talk, as always. So one question, did you look into the likelihood and the relation to your metric?
Oh, that's a great question. We didn't look at likelihood because, you know, in likelihood, when you look at likelihood, I feel like you're using generative models for a different purpose. For example, you may be using them to score different models in terms of generalization. But under all this talk, I assume that we're using generative models as a way to get new samples, a way to get new proposals for, you know, trajectories and model-based RL, or samples to do data augmentation, or samples for scientific discovery and things like that. And in that case, diversity becomes very, very, very important, and likelihood becomes less important. And so I feel like this metric would fill that gap. Yeah.
I thank you for the great talk. I'm curious how to think about sort of designing these kernels and whether the kernels that we have are measuring the right things, you know, in terms of how they affect the resulting measures of diversity.
Yes, that's a great question. We looked at actually looking at the influence of the choice of the kernel is an important thing that we should add. I agree with you. And we looked at, you know, defining the kernel just through the original samples using cosine similarity, or if it's a case of text, using BLEU score as a way to define the kernel. But we also looked at using, you know, what the other metrics use, which is, for example, for FID, using inception as a way of getting the features, new vectors, and using that to define similarity. We also explored that for the image experiments. So yes, there is, you have to define you have to decide how to define the kernel matrix, which similarity to choose, and which in the results show that even simply looking at directly at the original samples, using things like cosine similarity or BLEU scores as a way of defining similarity, capture intuition behind diversity very well. Yeah.
All right. Thank you so much.
Thank you.
Thank you for the talk, and I think we can have another round of applause.
Bye, everyone. Thank you.